Alright, what's going on in physics class? Let's get this party started. We only got 40 minutes and we got a lot to cover. I'm going to basically cover the rest of chapter 1 today if we possibly can. We got a new schedule in, and I think that I hang out with you for an hour and a half on Fridays and for 40 minutes on Wednesdays. So hopefully we can get through this. How are you guys doing? How's your brains? You guys alright? Yeah? Good? Can you hear my voice? Can you see my face? Is the audio good? Is it coming through? Alright. Then let's get everything started. Good. Alright. Can you see this? What does it say? There we go. Awesome. Alright. Let me just go grab some paper towels. There it is. Dry cloth. Much better. Alright. Oh wait, I can't see you. Oh, you're talking about the piece of glass that I usually use. Yeah, I put a painting. Justin, I'm going to have to turn your audio on. There. Alright. You're talking about the piece of glass I use. Yeah, the piece of glass I use is actually, I put a black thing in here because I'm using my Mac to record this. I had to switch up some things because of technical issues. I'm using my Mac to record this, and I don't know how to reverse the camera. So instead of using it as a clear board where I stand on one side and then show you guys and then have the camera reverse the image for me, I am using I just put a black picture behind me, and then I'm using it kind of like a whiteboard. It's not a whiteboard, it's a blackboard. It's weird, I know. Anyway, let's talk about significant figures. Remember what I told you guys about significant figures is a lot of times people will report a whole bunch of numbers. They'll just use whatever spits out of their calculator. I see this so much in engineering, and actually it kind of showcases, and they're trying to do it to showcase how smart they are. It's like, look at this calculation I made. It's got like 1 billion numbers. And then they write down every single thing thinking that like they're showcasing how smart they are. And really what it is to me is it's showcasing how dumb they are. It's showcasing how much they don't really understand like what's going on. Because like, imagine this, if you were to take your weight and multiply it by your age, alright? So I would be like, imagine if I wrote this down, my weight times my age. I wrote down 170, let's see. Let's do my weight divided by my age. How's that? My weight divided by my age. Alright? So let's go 170 divided by 32. So write that, use a calculator. Tell me what the answer is. 170 divided by 32. .31. Actually, you know what? Wait. What are you talking about? 7.353000. Is that you, Justin? Where are you writing that? Well, so what's the answer? Is it 170 divided by 32? What is that? Fine, I'll use my calculator. Oh no, not times. Divided by 32. 5.3125. Got it. 5.3125. 5.3125. Okay? And you write that down, you should be like, oh, that's the answer. And yes, technically that's the answer, but that's kind of dumb. It's kind of showcasing how dumb you are, because imagine this. You reported how many significant figures for me? 1, 2, 3, 4, 5. Did you really measure your weight up to 5 significant figures? Or is this a ballpark weight? Or even more, what even makes more sense to me is, did you really measure your age? Mr. Dalday, are you exactly 32? Like today was your birthday? And not only that, are you 32.000 years old? That means not only is today your birthday, it's the exact day, minute, second. No, I'm not exactly 32. My birthday was back in January, so technically I'm like 32.5. You know, if you want to get really technical about it, I can tell you the exact decimal up to 5 digits. But then, I hate to say this, but by the time I tell you the answer, the next second that number will change. So this number 32 is actually only accurate up to 2 significant places. Does that make sense to you now? So, yeah, exactly. Adding too many significant figures actually detracts from the accuracy of what the problem should be, because this number 32 is only reported to 2 significant figures. I can tell you exactly that I'm 32. I can't tell you that I'm 32.5784351, something like that. But I can tell you I'm at least 32. You know what I mean? Last time I checked, I think. So there is only 2 significant figures in this number right here. So in my answer, I should only report up to 2 significant figures. So I should only report those numbers, 5.3. Because that's how accurate my answer is. Now, I guesstimated 170, but what if I were 171 and I just wrote down 170? How many significant figures is in the number 170? One or two? How many significant figures is in this number right here? Only 2, exactly. These zeros don't count. But if I put a decimal, then it does count. Because that means I've measured it to exactly, I am 170 pounds. The webcam is on. I changed the view on your screen just now. Can you guys see it better? You guys can see the chat and the thing. I feel like I kind of took control of your window, which I think is how I'm going to be doing it from now on. Is that better now? Can you see the webcam? All right, awesome. So check this out. If I put 170, this is 3 significant figures because now the 0 does count. It's sandwiched between that decimal place. The better way to kind of represent that would be to say 1.70 times 10 to the 2. And that kind of gets into our next topic, which is scientific notation. This is a better way of representing the number of significant figures, because you can easily see anytime a 0 comes after the decimal place, that is counted as a significant figure. So 1.70 has 3 significant figures. Wendy, Julia, Justin, can you guys see the webcam? Can you see my face? All right. Kiko, that might be a personal problem, and I don't mean that like it's a personal problem, but you might have to log out and log back in. It might be your personal computer's problem. Not like a personal problem as in like you have a bad habit or something. You know, I don't know what I'm talking about. Anyway. So what you do is when you multiply out or divide out things, you need to make sure to take only the smallest amount of significant figures you have. Now, I'll admit to you, in chemistry, they make a big deal out of this. Why? Because you're actually measuring the amount of chemicals and whatnot. In physics, I will make a point to make sure I teach you this, but I'm not going to be like crazy about this. If the answer's supposed to be 2 significant figures and you end up reporting 3, okay, I'm fine. Just don't report something stupid like 10 significant figures. Because to me, that signifies that you don't understand what you're talking about. Does that make sense? Which is, I'm not saying that you're stupid, but for doing that, I'm just saying like you kind of need to logically think about how accurate that answer should be. We cool? Yes, we can move on. Moving on. All right, so we got significant figures. Significant figures rules. You guys probably covered this in chemistry. I'm going to read them off to you real quick. I'm just going to move on. We don't need to have a full discussion about it. All right. Leading or trailing zeros can make it hard to determine the number of significant figures. How many significant figures are in this number? I would take a look at this and say, all right, 2, 5. All right, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 significant figures in this number, and I have no idea why they put a comma after there. Oh, I get it. They're 2 separate numbers. Okay, so the first number is 2500. That only has 2 significant figures. This number right here, 0.000036, also only has 2 significant figures. No, there are only 2 in both of them. Now, if you put a few more zeros after that 36, then it would have 1, 2, and however many zeros you add. But as it stands, that one on top only has 2 significant figures. Scientific notation writes these numbers from 1 to 10 multiplied by a number of 10, making the number a significant figures much clearer. For example, 2.5 times 10 to the third is 2500, and that is, you can easily see 2 significant figures. Same as over here, 3.6 times 10 to the negative 5 is the same as 0.000036, which is 2 significant figures. It's almost like scientific notation makes it easy to see right off the bat. All right, the significant figures, there's a round-off error. The last digit in a calculated answer may vary depending on how it was calculated due to rounding off the insignificant digits. For example, if you have 2.21 or $21 and you want to add 8% tax, that answer will be 2.38. So if I bought something for $2.21 and I add 8% tax to it, then I'm going to have to pay $0.3868 cents. So that's like $2.39. Because you would round it off to 3 significant figures because the first one has only 3 significant figures to begin with, so therefore you only keep 3 significant figures. Does that make sense to you? Right, and you would round it off because you say, okay, the cutoff is right here at the 8, and so therefore I'm going to round this. I look at the next figure down, and I round it up to a 9. All right, let's see, what about this one? $2.21, you want to add $1.35 and you get $3.56. That's not helpful. I mean, that does so. What? I don't care. All right, $3.56 plus 8% tax is $3.84. I'm sure that's not. I'm sure that is not exactly 84 cents. I'm sure they had to round it at some point. All right. Converting units. This is actually really important stuff, and I think that we should go through this as much as possible. And then today, what my plan is to finish chapter 5 or chapter 1. If I can get through, let's see. I need to talk about scalars and vectors, order of magnitude calculations, solving physics problems, and then we can just move on. So today, my goal is to get through all of chapter 1 and finish that off. Then on Friday, what I want to lecture about is doing Fermi problems. Fermi problems are incredibly fun and extremely fun. I actually like them a lot. Let me explain to you. All right, let's do converting units. So, 1 meter equals 3.281 feet. Ask me, am I going to ask you to memorize all of these conversion factors? Remember, I told you to ask me. Come on, ask me. Get your finger muscles working and start typing to me. Do we need to memorize all these conversion factors? I would say no. You would look them up in a table. But you need to learn how to use that table. That's important. Not only that, there is a few that I want you to memorize. I want you to know how to convert a meter into a centimeter, and vice versa. I want you to know how to convert, anytime you have the word centi, deci, pico, that kind of stuff, you know where we're adding suffixes? That's where I want you to figure out how to convert those. I also want you to memorize this one. Let me look it up real quick. I do have it memorized. I just don't want to tell you the wrong one. Inches to cm. Yeah, that's it. I remember. All right. I want you to memorize this one, so write it down. 1 inch. Sorry. Okay. 1 inch is equal to 2.54 centimeters. You got it? Memorize that. That's important. What trips me out about that is that's an exact number. I mean, I can get this answer right here from here. I want to figure out, let's say I want to figure out how many meters, how many feet is in a meter. And if you get a meter stick and a yardstick, you'll find that the meter stick is just a little bit bigger than the yardstick because the yardstick is only 3 feet long, whereas the meter stick is apparently 3.281 feet long. But say I only know this one, and I want to figure out, I want to go from meters to feet. Well, here's how you do it. You do this kind of stuff like this. Start off with 1 meter. Got it? Now I want to convert this. So 1 meter, can we bring a meter down to centimeters? Well, the way we would do this conversion, and you should have learned this back in chemistry, is make this big parentheses over here, and we'd say, all right, 1 meter is 100 centimeters. You guys know how to do this, right? You guys are writing notes, taking notes? Good. All right, so 1 meter equals 100 centimeters. Now, once I have centimeters, I can convert that to inches. So, .54 centimeters equals 1 inch. How do I know that? Because I had this one memorized. Got it? Now let's go from inches to feet. You know how to do that. 12 inches equals 1 foot. Now, someone pull out a calculator. Take 1, multiply by 100, divide by 2.54, divide that number by 12, and hopefully the answer you'll get is 3.281. Tell me what the answer is you get. Take 1, multiply by 100, use your calculators. 1 times 100, divide by 2.54, divided by 12. If you don't know how to use your calculator, type it into Google Chrome. It will tell you the answer. Just take 1, asterisk 100, divide 2.54, divide 12. What's the answer? I want you guys to chat it to me. 3.281000000. 3.2810000. That kind of stuff. Now here's the cool thing, all right? Here's the thing that kind of trips me out. If we were to worry about significant figures, do we report 3.281? What is the guessed number in here? All right, Julia says 3.28. You scratch the 1 and there's a bunch of zeros. I agree. Why, Julia? Why would I only keep 3 of my significant figures? I mean, look at this. There's 12, the number 12. That only has 2 significant figures. So why am I keeping 3 of them? Go for it. One of you guys can talk. Talk. Just press the talk button down and start talking. Why am I only keeping 3 significant, or why do I keep 3 significant figures? Because look over here. The smallest amount of significant figures we have is 2. Actually, the smallest amount we have is 1. Because in 100, there's only 1 significant figure. Do you guys agree? Because those numbers we use in our conversion, one of the numbers... okay, all right. I think I see what Julia is getting at. Julia is saying yes, but look at this one. This one has 3 significant figures, and that's used in our conversion factor. The other number that's used in our conversion factor is this 100, which, yes, it technically does only have 1 significant figure, but it actually has infinite significant figures. Because the point that we're trying to make, and Kiko, you're gonna have to mute. Sorry. The point that I'm trying to make is this. There are exactly 100 centimeters in a meter. That is not a guessed answer. That's not approximately 100 centimeters in a meter. That is an exact number. So we don't worry about the number of significant figures from here. Does that make sense to you now? There are also exactly 12 inches in a foot. There's not 12.5. There's not about 12. There's exactly... A foot is defined by 12 inches. So, we don't worry about, like, we don't say, hey, we're going to truncate our answer down to 2 significant figures because, look, there's the number 12 only has 2 significant figures. No, this is an exact answer. It doesn't contribute to our significant digits. This is an exact answer. It doesn't contribute to our significant digits. This right here is kind of a guessed answer. Because is there exactly 2.54 centimeters in 1 inch? It could be a little bit off. So there's only 3 significant figures here. So our answer should only reflect 3 significant figures. Cool? Does that make sense to you? Does that make sense to everyone? I want everyone to chime in. Yes, no, I don't get it. What's your thoughts? Come on. All right, Julia's talking. I can see you. All right. Okay. Good. Now that you have that locked into your brain, I hate to say this, but what I just said was wrong. The answer is actually this. This is an exact conversion. Why? Actually, what it is you should probably just write down this. There is exactly 1 meter is 3.281 feet. The reason being is this. The reason why I told you to memorize this one right here is because someone went into the rule book and defined 1 inch is exactly 2.54000000 infinite zeros centimeters long. That is how they defined the conversion from centimeters to inches. So technically this is an exact conversion now as well. But that's the only one that happens like that. Everything else is a little bit off. Everything else you have to worry about the number of significant figures in your conversion factor. But 1 inch is defined as exactly 2.54 centimeters. Does it make sense now? But I agree with your logic. I agree with your logic. If we didn't know that fact, then we would have just had to round this off to 3.28 and drop that 1 at the end. Because that 1 isn't a part of, because if we didn't know that 1 inch is exactly 2.54 centimeters, then we would have had to only report 3 significant figures, because this measurement is only accurate up to 3 significant figures. Am I making sense, or am I talking crazy? What are your thoughts? All right, I got a lot of slides to cover. I got like 5 minutes to do it, or 10 minutes to do it. Order of magnitude calculations. I love these questions. Let me come back to them, because scalars and vectors. All right. Why don't we do this? Why don't we talk about the order of magnitude calculations? I'm going to go over this on Friday. I'm erasing, by the way, so take a computer screenshot of your thing if you want to see what the screen looks like. Just hold down the control button on top of your Chromebook and press the button above the 6 key, and that would take a screenshot. I'll even stand like this a little bit. All right, you guys done with the screenshot? I'm done. I'm going to erase. So I erased pretty quickly, but I expect you guys to be able to take notes or do a screenshot. Sorry, it's tough to erase these things. Let me just get it out. There we go. All right, so check this out. Once upon a time, when I was getting a job, I'm going to talk to you guys. I'm going to teach you guys through a story. Got it? Once upon a time, I was getting a job, and I was trying to interview for this position as a lab technician for Loyola Marymount University. At the end of the interview, after the guy asked me all about, like, because I recently graduated from Berkeley, you know, I had a physics degree. At the end of the interview, the guy asked me, he said, you know, I have one last question to ask me. And I said, shoot, because I did a really good interview. I was really pleased. I got the job, by the way. But he said, I have one last question to ask you. And I said, yeah, go for it. And I want you to type up your reactions. Once I ask you the question, tell me what you think. You say, what? Or that's cray-cray, or I can totally do that. But anyway, here's what he asked me. He said, how many barrels of crude oil is shipped into the United States every year? Respond. Come on, you guys, I'm waiting on you. Is that what you said, Julia? You would have gone in a lot or way too much? That's the answer you would have gone for? You're interviewing for a technical science position here. You have a degree in math or physics or whatever. The question is, how many barrels of crude oil is shipped into the United States every year? All right. I think that my initial response to it, and I didn't say this, I thought it in my head. I said, what? What are you talking about? I'm thinking, this guy's crazy. Does he think I'm Wikipedia or something like that? And then I said, okay, wait, calm down, Tosh. You need to be able to kind of, you can't say you're crazy in an interview and get the job. So I said, all right, well, let me think about that. I know in my head, according to the United States Census, there are about 300 million people in the United States right now. Got it? 300 million people. And I would say that there's probably one car for every 3 people. We've got big families. Not everyone owns a car. I suppose like maybe a fifth of the population is kids, and kids don't, or maybe people under 20, and everyone under 20 doesn't own a car. So I'd say 1 in 3 people own cars in the United States. Is that about fair? And let's say that the average person in the United States walks, or not walks, but drives to work, and they drive, I don't know, like 10 miles. Let's say 5 miles to work, 5 miles back. And I'm just guessing here. So that would mean they drive 5 miles to work, 5 miles back. That would mean they drive about 300 miles to work and back per year. Okay, that sounds a little bit low. Let's go with 500 miles to work, to drive around. You add 500 miles to your car every year. All right? So how many gallons of gasoline are they burning up? Well, your car gets about 20 miles to a gallon. I would say a good car, sedans get like 25 miles, whereas like SUVs get like 10 miles to a gallon. So I would say maybe 20 miles to a gallon. Let's approximate that. So from that, you could figure out how many barrels of crude oil is shipped in. The only answer I told the guy, I said, the only answer I really don't know is how many gallons of gasoline you get out of 1 barrel of crude oil. But if you could tell me that, I could tell you your exact answer. Okay, so let's kind of think about that. We have 300 million people. So that would be 3 times 10 to the, all right, so that would be 300 million. So the million is 6, so that would be 8. We have that many people in the United States, 300 million, okay? Then we divide that by, this is people. Then I'm going to divide that by 3 people per 1 car. I'm setting up a unit conversion here. 300 million people, 300, or divide that by 3 and you get 1 car. So there's 1 million cars. And then you say, okay, well then I'm going to multiply that by 1 car gets 500, goes 500 miles every year to get to work and whatever. So then I have 500 million miles that I'm driving with all the people in the United States. And then I take that and I divide that by the number of miles. So I have 500 million miles so far. So that would be 5 times 10 to the 8. Divide that by, so this is miles per gallon. And how many did I say? I said 20. So what is 500 million divided by 20? What is 500 divided by 20? What is 100 divided by 20? It would be 5 times 5, that's 25. So that's 20, okay wait, 25 times 10 to the 6. So apparently America uses 25 million gallons of gasoline every year. So let's say that it takes, if you ship in 1 barrel of crude oil, you can make 100, let's just pretend 100 gallons of gasoline. Then that would mean 25 times 10 to the 4. So that would be 25 with 4 zeros after it. You're looking at 2, 5, 1, 2, 3, 4. 250,000 barrels of crude oil. Or 2.5 times 10 to the 5th power. Does that make sense? But here's the point. I got the job. Was my answer correct? It actually wasn't that far off. My answer was, I guessed 2.5, and I think the answer was like 3. So I was like not that far off. But the point that I got is, he was like, dude, you got the right number of zeros. That's awesome. That is so cool. You got the right number of how many zeros you need to add, because that's the important one. The number 3 doesn't matter. The 8 makes a much bigger difference, right? So what he said is, he said, I wanted to see your perseverance in math. I wanted you to, you're going to be faced with a lot of problems in this job, and I want you to be able to approach these problems with logic. I don't want to see you get scared and run away and say, I don't know, and then come to me and try to get the answer. Because I am going to hire you because you can think. And I'm not going to try to do your job for you. That's what he told me. So because I'm hiring you and I want you to think, I need you to, well, I need you to think. I need you to approach a problem and work at it. Does that make sense? So that's order of magnitude calculations. We'll do a lot more of them, and they're going to be a lot of fun, I'll be honest with you. I really enjoy these. But that was my interview. This is my story about how to introduce order of magnitude calculations. Because I've never had a problem like that before in my life. And then he just told me, how many gallons or how many barrels of crude oil are shipped into the United States? And I said, oh, okay, well, 2.5 times 10 to the 5th power. Answer was 3 times 10 to the 5th power. I was happy. And I'll be honest with you, I don't know if I made the same exact assumptions as I made back then. So if you look it up on Wikipedia, it might be wrong. It might be different or whatever. But the point I'm trying to make here is that, all right, here, let me tell you one more story and then I'll leave. Okay, I got 5 minutes. Technically, I need to finish class at 11:55, but deal with it. All right? Where this came from is this dude, his name was Enrico Fermi. He was an awesome, awesome physicist, one of my favorite mathematicians, but he worked on a big project that was a big, bad project, I feel. You know, I feel like it's kind of like socially not responsible. He basically helped create the atomic bomb. Now, there's going to be a lot of like moral things we can discuss with this, but here's what he did. When they were testing out the bomb in New Mexico, he took out a piece of napkin and he ripped it up into small pieces, and then the bomb went off, and then he dropped it, and he saw that the paper went backwards. When it fell, it didn't fall straight to the ground. The little strips of paper kind of flew backwards. That's because of the blast of the thing. And then he looked at that and he said, about 300,000 pounds of TNT. That's what he said. It took him a couple of minutes. I think he wrote on the back of the napkin, and he said, okay, about 300,000 pounds of TNT. That's how big the atomic bomb was, right? And then 3 months later, the other scientists went in and then like calculated out all of these things. It ended up being like 295 pounds of TNT, or 1,000 pounds of TNT. So he was like off by like 500, you know, by the number 5, but he had the exact same number of thousands of pounds. And so from then on, these order of magnitude calculations are called Fermi problems, because Fermi was a master of this. So that's what this guy was asking me. He was asking me a Fermi problem. He was saying, how many, like, take a guess. Don't just say, I don't know. Take a guess. If I ask you how many popcorn kernels are inside of how many grains of rice is inside of your 25-pound bag of rice, you guys shouldn't look at me and say, I don't know. You guys should say, well, let me think. I could fit 100 grains of rice into a bowl. Something like that. 1,000 grains of rice in a bowl. I can have this many bowls. I would guess this many grains of rice inside the bag. To the right order of magnitude. And the order of magnitude is exponent, which is kind of the only important number when it comes to doing these calculations. All right, anyway, I'm out of time. I'll talk to you later. Have fun with physics. I'm done with chapter 1. You guys can move on to chapter, or I think that next week we're going to cover Fermi problems, so that's going to be a lot of fun. Wow. Justin Elliker, you counted the number of grains of rice inside of a 25-pound bag? I'm glad I got that on recording, because that's almost like classic right there. I'll talk to you later, Justin. I love you, man. All right, goodbye.